Right now at the center of your galaxy, something is lurking in absolute darkness. It weighs as much as 4 million suns compressed into a region smaller than the orbit of Mercury. It does not emit light. It does not reflect light. It is a tear in the fabric of space-time itself, a place where the universe folds inward and nothing, absolutely nothing, can escape. Not matter, not energy, not even light traveling at its maximum cosmic speed of 300,000 kilometers per second. This is Sagittarius A, the supermassive black hole at the heart of the Milky Way. And it is just one of billions of such objects scattered throughout the observable universe. Some are small, mere 3 times the mass of the Sun, leftovers from dead stars that collapsed under their own gravity. Others are monsters, billions of solar masses, powering the most luminous objects in the cosmos while remaining themselves invisible. Black holes are the darkest places in the universe not because they lack illumination, but because they trap light itself. They are regions of space-time so severely warped that the normal rules of physics break down. Inside a black hole, space and time trade places. Directions lose meaning. The future becomes a location, and that location is the center, the singularity, the point where everything that falls in must inevitably go. Albert Einstein's equations predicted black holes in 1915, though Einstein himself refused to believe they could actually exist. The mathematics was undeniable, but the implications seemed too extreme, too bizarre, too violent a distortion of reality. Surely nature had some mechanism to prevent such objects from forming. Surely the universe would not allow space-time to be torn apart this way. But the universe does not care about human intuition. Black holes exist. We have observed them indirectly through the motion of nearby stars, through gravitational waves rippling across space-time when they collide. We have observed them indirectly through the motion of nearby stars, through gravitational waves rippling across space-time when they collide, through jets of superheated matter shooting from their surroundings. In 2019, the Event Horizon Telescope captured the first actual image of a black hole shadow, a dark circle silhouetted against glowing matter, confirming what mathematics had predicted a century earlier. If you are ready to explore the darkest places in the universe, to understand what happens when gravity becomes so intense that escape is not just difficult, but physically impossible, then settle in. Get yourself comfortable. Let's descend into the darkness, into places where the very notion of leaving ceases to have meaning. Every black hole, regardless of its size or origin, shares the same basic anatomy. At its heart lies the singularity, a point of infinite density where all the mass of the black hole is concentrated. Surrounding this singularity is the event horizon, the boundary beyond which escape becomes impossible. And extending outward from the event horizon is the severely warped space-time that defines the black hole's gravitational influence. But these dry technical terms do not capture the strangeness of what a black hole actually is. Let us build the picture carefully, starting with the event horizon, the point of no return. The event horizon is not a physical surface. It is not made of matter. You could pass through it without touching anything solid. It is simply a boundary in space-time, a mathematical surface that divides the universe into 2 regions, the region where escape is possible and the region where it is not. Think of it not as a door, but as a one-way membrane in time itself. Once you cross the event horizon, all paths through space-time lead inward. You cannot turn around. You cannot fire rockets powerful enough to reverse your trajectory. You cannot fire rockets powerful enough to reverse your trajectory. You cannot do anything that would bring you back across that boundary. Not because some force prevents you, but because back no longer exists in any meaningful sense. Inside the event horizon, all of space-time is tilted toward the singularity. Every direction you could move, every path you could take through space, leads closer to the center. The future, which normally spreads out in many possible directions, collapses to a single inevitable destination. You will reach the singularity. There is no avoiding it, just as you cannot avoid moving forward in time in normal space. Inside a black hole, moving toward the singularity is like moving into the future. It is not a choice. It is the structure of space-time itself. The location of the event horizon is determined by the black hole's mass. The relationship is precise and simple. The more massive the black hole, the larger its event horizon. This radius is called the Schwarzschild radius, named after Karl Schwarzschild, who derived the first exact solution to Einstein's equations describing a black hole. For any mass, you can calculate its Schwarzschild radius, the size it would need to be compressed to in order to become a black hole. For Earth, that radius is about 9 millimeters. Compress the entire planet into a sphere less than 2 centimeters across, and it becomes a black hole. For the Sun, the Schwarzschild radius is about 3 kilometers. Compress all the Sun's mass into a ball roughly the size of a small town, and it too becomes a black hole. These are not practical prescriptions. No known process can compress Earth or the Sun to such densities. But they illustrate an important point. Black holes are not exotic matter. They are ordinary matter compressed to extraordinary densities. Every object has a Schwarzschild radius. Every object has a Schwarzschild radius. Most objects are much larger than their Schwarzschild radius, so they do not form black holes. But if you could compress them enough, they would. The density required to create a black hole depends on the mass. For stellar mass black holes, roughly 3 to 100 times the Sun's mass, the density is incomprehensibly high. The matter is crushed beyond nuclear densities, beyond anything we can reproduce in laboratories. But for supermassive black holes, millions or billions of solar masses, the average density can actually be quite low, comparable to water or even air. This seems paradoxical until you realize that density is mass divided by volume, and volume grows as the cube of radius. A black hole with the mass of 4 million suns has a Schwarzschild radius of about 12 million kilometers, roughly the size of Manhattan stretched to cosmic scales. Spread 4 million solar masses throughout that volume, and the average density is not particularly extreme. But average density is misleading. All the mass is concentrated at the singularity. The vast volume inside the event horizon is mostly empty space-time, falling inward, doomed to reach the singularity, but not yet there. The singularity itself has infinite density, all the mass compressed to a single point with zero volume. This is where physics breaks down. General relativity, Einstein's theory of gravity that predicts black holes in the first place, fails at the singularity. The mathematics produces infinities, undefined quantities, predictions that make no sense. Infinite density, infinite space-time curvature. These are not physical realities, but signals that the theory has reached its limits. Most physicists believe that quantum mechanics, which governs the behavior of matter at the smallest scales, becomes important at the singularity. Most physicists believe that quantum mechanics, which governs the behavior of matter at the smallest scales, becomes important at the singularity. A theory of quantum gravity, which would unify quantum mechanics and general relativity, is needed to describe what actually happens at the center of a black hole. But we do not have such a theory yet. String theory, loop quantum gravity, and other approaches offer possibilities, but none are confirmed. So the singularity remains mysterious. We know it must exist based on the mathematics of general relativity. We know matter falling into a black hole must reach it, but we do not know what happens when it arrives. Does the matter truly compress to a point of infinite density? Does quantum mechanics prevent the formation of a true singularity, creating instead some ultra-dense but finite structure? Does the singularity hide multiple universes, wormholes, or other exotic phenomena? These questions remain unanswered. The event horizon shields the singularity from observation. Nothing that happens inside can send a signal out. The singularity could contain anything, obey any physics, and we would have no way of knowing from the outside. But we can understand what happens approaching the event horizon, even if the singularity remains mysterious. And what happens is strange enough without invoking unknown physics. Black holes come in several varieties, classified by mass and origin. The most common are stellar mass black holes, formed when massive stars collapse at the end of their lives. Stars more than about 20 times the Sun's mass end their existence in supernova explosions, blowing off their outer layers while their cores collapse. If the remaining core exceeds roughly 3 solar masses, no known force can support it against gravitational collapse. It implodes, crushing matter to nuclear densities and beyond, forming a neutron star or, if massive enough, continuing to collapse into a black hole. It implodes, crushing matter to nuclear densities and beyond, forming a neutron star or, if massive enough, continuing to collapse into a black hole. These stellar mass black holes range from roughly 3 to perhaps 100 solar masses. Anything less massive forms a neutron star instead. Anything more massive is rare because very massive stars lose so much mass during their lives that their cores typically do not retain enough mass to form black holes heavier than a few dozen solar masses. Stellar black holes are scattered throughout galaxies, invisible in isolation but detectable when they have companion stars. Matter pulled from the companion forms an accretion disk around the black hole, heating to millions of degrees and emitting intense X-rays as it spirals inward. These X-ray binaries reveal black holes throughout our galaxy and others. At the opposite extreme are supermassive black holes, millions to billions of solar masses, lurking at the centers of most large galaxies. Sagittarius A in the Milky Way is modest compared to some. The black hole at the center of galaxy M87, the first black hole ever imaged directly, weighs about 6.5 billion solar masses. Others exceed 10 billion solar masses, dwarfing entire star clusters. How supermassive black holes form remains partially mysterious. They were already in place when the universe was very young, less than 1 billion years after the Big Bang. Growing 1 billion solar mass black hole in such a short time requires either starting with very massive seeds or accreting matter at extraordinary rates. Both processes face theoretical challenges, and the details remain actively researched. Between stellar and supermassive black holes lies a mysterious gap. Intermediate mass black holes, roughly 100 to 100,000 solar masses, should exist based on theoretical models, but they are difficult to detect and confirm. Intermediate mass black holes, roughly 100 to 100,000 solar masses, should exist based on theoretical models, but they are difficult to detect and confirm. Recent observations suggest they might lurk in dense star clusters or globular clusters, but their population and properties remain uncertain. Finally, there are hypothetical primordial black holes, formed in the early universe from density fluctuations shortly after the Big Bang. These could range from microscopic, smaller than atoms, to thousands of solar masses. If they exist, they could account for some or all of the mysterious dark matter that makes up most of the universe's mass. But no primordial black holes have been definitively detected, and their existence remains speculative. All these types share the same fundamental structure: event horizon, singularity, warped spacetime. The physics that governs them is identical, differing only in scale. A stellar black hole and a supermassive black hole are the same kind of object, just vastly different in size and mass. But size matters when considering what happens to objects that fall in. The tidal forces, the difference in gravitational pull between your head and your feet, depend not just on the black hole's mass, but on how close you are to the center. For a stellar mass black hole, the event horizon is so close to the singularity that tidal forces at the horizon are enormous, capable of ripping apart any object long before it crosses into the darkness. For a supermassive black hole, the event horizon can be millions of kilometers from the singularity, and tidal forces at the horizon might be barely noticeable. You could cross the event horizon without feeling anything unusual. This is one of the paradoxes of black holes. The smaller, less massive ones are in some ways more violent and destructive at their boundaries. The larger, more massive ones offer a gentler passage across the point of no return, at least initially. The larger, more massive ones offer a gentler passage across the point of no return, at least initially. The destruction comes later, deeper inside, as you approach the singularity where tidal forces grow without limit regardless of the black hole's size. Understanding why nothing can escape a black hole requires understanding escape velocity, the speed needed to break free from a gravitational field. On Earth, escape velocity is about 11 kilometers per second. Launch something at this speed or greater, and it will escape Earth's gravity and never fall back. Launch it slower, and it will eventually fall back to the surface. Escape velocity depends on mass and radius. The more massive an object, the higher its escape velocity. The smaller its radius, the higher its escape velocity. Earth's escape velocity is 11 kilometers per second. The Sun's escape velocity, measured from its surface, is about 618 kilometers per second. A neutron star, with similar mass to the Sun but compressed to a radius of about 10 kilometers, has an escape velocity around 100,000 kilometers per second, about 1/3 the speed of light. A black hole's escape velocity, measured from the event horizon, is exactly the speed of light, 299,792 kilometers per second. This is the cosmic speed limit. Nothing can travel faster than light. Therefore, nothing can escape from the event horizon. But this is a simplified picture. Escape velocity is a Newtonian concept, useful for everyday objects but inadequate for black holes where spacetime itself is warped. The real reason nothing escapes is not that the required speed exceeds light speed, but that spacetime inside the event horizon is structured such that all paths lead inward. Think of it this way. Normally, spacetime is like a flat landscape. You can move in any direction: north, south, east, west, forward and backward in time. North, south, east, west, forward and backward in time. But near a black hole, spacetime warps. It becomes like a funnel, curving downward toward the center. The closer you get, the steeper the funnel becomes. At the event horizon, the funnel becomes vertical, not tilted steeply, but actually vertical in the time dimension. Inside the event horizon, moving outward in space is like trying to move backward in time. It is not just difficult, it is forbidden by the structure of space-time itself. You can no more escape a black hole from inside the event horizon than you can travel into the past in normal space. This is why light cannot escape. Light follows the shortest paths through space-time called geodesics. Outside the event horizon, some geodesics lead outward, away from the black hole. At the event horizon, all geodesics either plunge inward or, at best, orbit endlessly at the horizon itself, going neither in nor out. Inside the event horizon, all geodesics lead to the singularity. There are no paths that lead back out because the structure of spacetime does not permit them. Imagine spacetime as a river. Outside the event horizon, the current flows toward the black hole, but you can swim against it if you are fast enough. At the event horizon, the current flows at exactly the speed of light. Even light itself cannot make progress against this current. Inside the event horizon, the current exceeds light speed, sweeping everything inexorably toward the singularity. But this analogy is imperfect. The current is not flowing through space. Space itself is falling inward. The event horizon is the surface where space is falling inward at the speed of light. Inside, space falls inward faster than light. carrying everything with it regardless of how fast it tries to move outward. This leads to another paradox: time dilation. As you approach the event horizon, time slows down from the perspective of a distant observer. As you approach the event horizon, time slows down from the perspective of a distant observer. This is a consequence of general relativity, confirmed by countless experiments with GPS satellites, atomic clocks on airplanes, and other precision tests. Near a black hole, time dilation becomes extreme. At the event horizon, time effectively stops from the perspective of someone watching from a safe distance. An object falling toward the event horizon appears to slow down, taking longer and longer to fall each successive meter. As it approaches the horizon, it appears to freeze, hanging there forever, never quite crossing. But this is only from the outside perspective. From the perspective of the falling object, time passes normally. It crosses the event horizon in finite time, seconds or minutes or hours depending on the black hole's size, and continues falling toward the singularity. There is no freezing, no slowing. The journey ends quickly and definitively. This creates two incompatible descriptions of the same event. From outside, the object never crosses the event horizon. It freezes at the boundary, its image redshifted to invisibility as light struggles to escape the intense gravity. From inside, the object crosses smoothly and falls to its doom within a short time. Both descriptions are correct in their respective frames of reference. There is no absolute answer to whether the object crosses the horizon because the question depends on perspective. Relativity allows different observers to have different, equally valid descriptions of events, and this is one of the most dramatic examples. Understanding black holes requires accepting these paradoxes, these multiple perspectives that seem contradictory but are both true. The universe is stranger than common sense suggests. Black holes are the places where this strangeness becomes most extreme, where space-time warps so severely that normal intuitions fail completely. The universe is stranger than common sense suggests. Black holes are the places where this strangeness becomes most extreme, where space-time warps so severely that normal intuitions fail completely. And we have only begun to explore what happens when you approach and cross the event horizon. The journey into darkness holds even stranger revelations about the nature of space, time, and the limits of physical law. To truly understand why black holes are inescapable, we must go deeper into the physics of curved space-time and confront what happens when gravity becomes strong enough to trap even light itself. The mathematics is precise, but the reality it describes defies everyday experience. Let us build the understanding step by step, from familiar concepts to the exotic physics that governs the darkest places in the universe. Begin with the concept of space-time curvature. In Newton's picture of gravity, massive objects exert forces on other objects, pulling them together across empty space. The sun pulls on Earth. Earth pulls on the moon. This pulling force depends on mass and distance according to a simple inverse square law. Einstein's general relativity replaces this force with geometry. Massive objects do not pull on other objects directly. Instead, they curve the fabric of space-time itself. Objects then move along the straightest possible paths through this curved space-time, and these paths appear to us as gravitational attraction. The analogy commonly used is a rubber sheet stretched flat. Place a heavy ball on the sheet, and it creates a depression. Roll a marble near the depression, and it curves toward the ball, not because the ball pulls on it, but because the sheet is curved. The marble follows the straightest path it can through the curved surface, and that path curves around the depression. This analogy is helpful but limited. Space-time is not a two-dimensional surface, but a four-dimensional structure. But the basic principle holds: mass curves space-time, and objects move along the straightest paths through curved space-time. The more mass concentrated in a region, the more severe the curvature. And when mass is concentrated enough, the curvature becomes so extreme that space-time essentially tears, creating a region from which no paths lead back out. This is a black hole. Not a particularly dense object sitting in flat space-time, but a place where space-time itself has been warped beyond recognition, folded inward so completely that the interior is causally disconnected from the exterior. Light plays a special role in understanding black holes because light defines the structure of causality in space-time. Light travels along paths called null geodesics, the boundaries between what can influence what. If light can travel from event A to event B, then A can causally affect B. If light cannot travel from A to B, then A cannot affect B in any way. Causality is limited by the speed of light. The event horizon is the boundary where light becomes trapped. Outside the event horizon, light emitted outward can escape to infinity. It might be redshifted by gravity, its wavelength stretched and energy reduced, but it escapes. At the event horizon, light emitted outward neither escapes nor falls in. It orbits endlessly at the horizon, marking the boundary. Inside the event horizon, even light emitted outward falls inward toward the singularity. This means that inside a black hole, the future direction is inward. Time and space trade roles in a sense. Normally, you are free to move in any spatial direction, but must move forward in time. Inside a black hole, you must move inward in space, just as you must move forward in time. The singularity is not a place in space that you might avoid. It is a moment in your future that you must inevitably reach. The singularity is not a place in space that you might avoid. It is a moment in your future that you must inevitably reach. Let us make this concrete by following a photon, a particle of light, as it approaches a black hole. From far away, the photon travels in a straight line. It is not affected by the black hole's gravity because it is too distant, but as it gets closer, its path begins to curve. If the photon passes at a safe distance, its path bends slightly around the black hole and then straightens out again as it moves away. The black hole acts like a gravitational lens, bending light paths but allowing them to continue. If the photon passes closer, within about 1.5 times the Schwarzschild radius, its fate depends on its exact trajectory. There is a region called the photon sphere where light can orbit the black hole in a circular path. This orbit is unstable. The slightest perturbation sends the photon either spiraling in toward the event horizon or flying out to infinity. If the photon is aimed directly at the black hole or passes within the photon sphere, it falls inward. As it approaches the event horizon, something strange happens from the perspective of a distant observer. The photon's progress appears to slow down. It takes longer and longer to fall each additional meter. This is gravitational time dilation. Time passes more slowly in strong gravitational fields. Near the event horizon, time dilation becomes extreme. From the distant observer's perspective, time effectively stops at the horizon. The photon appears to freeze, hanging just outside the event horizon forever. But this is only how it appears from outside. From the photon's perspective, if a photon could have a perspective, the journey is brief and uneventful. The photon crosses the event horizon in finite proper time and continues falling toward the singularity. The photon crosses the event horizon in finite proper time and continues falling toward the singularity. There is no freezing, no infinite delay. The crossing happens. Once across the event horizon, the photon's fate is sealed. All its future paths lead to the singularity. It cannot turn around. It cannot orbit. It cannot escape. The structure of space-time inside the event horizon is such that the singularity lies in the future of every event, just as tomorrow lies in the future of today. Now consider what this means for the photon's wavelength and energy. As a photon climbs out of a gravitational field, it loses energy. Its wavelength stretches, shifting toward the red end of the spectrum. This is called gravitational redshift, and it has been measured precisely using laboratory experiments and astronomical observations. For a photon approaching the event horizon from inside, trying to escape outward, the redshift becomes infinite. The wavelength stretches to infinity. The energy approaches zero. The photon becomes undetectable even in principle because its energy falls below any possible measurement threshold. This is why the event horizon is dark, not because it absorbs light, but because light trying to escape from the horizon is redshifted to zero energy. The photon still exists, technically, but it has been drained of all energy by the act of trying to climb out of the extreme gravitational field. From outside, matter falling toward a black hole appears to slow down, dim, and redshift as it approaches the event horizon. The last light we see from the falling matter becomes infinitely redshifted, stretching to radio wavelengths, then longer, then undetectable. The matter appears to freeze at the horizon, its image fading to black as photons can no longer reach distant observers. But again, this is only the outside view. From the matter's perspective, nothing special happens at the event horizon. From the matter's perspective, nothing special happens at the event horizon. It crosses smoothly and continues falling. The event horizon is a global property of space-time, not a local property. You cannot detect it by local measurements. If you were falling into a supermassive black hole, you would cross the event horizon without feeling anything unusual. This creates a profound asymmetry. From outside, the black hole is a dark, frozen object, matter piling up at the event horizon but never quite crossing. From inside, the black hole is a dynamic, violent place where matter falls freely toward inevitable destruction. Both views are correct in their respective frames of reference, but they cannot be unified into a single consistent picture because the event horizon breaks the ability of information to flow between inside and outside. The strength of gravity at the event horizon depends on the black hole's mass in a counterintuitive way. For a stellar mass black hole, say 10 solar masses, the Schwarzschild radius is about 30 kilometers. The gravitational field at the event horizon is extraordinarily intense, producing enormous tidal forces that would rip apart any ordinary object. But for a supermassive black hole of 1 billion solar masses, the Schwarzschild radius is about 3 billion kilometers, roughly 20 times the Earth-Sun distance. The gravitational field at the event horizon is correspondingly weaker. The tidal forces at the horizon might be barely noticeable to a human-sized observer. This seems backward. The more massive black hole has weaker gravity at its event horizon. Yes, because the event horizon is farther from the center. Tidal forces, the difference in gravitational pull across an object, decrease with distance from the source. A supermassive black hole's event horizon is so far from the singularity that tidal forces there are mild. A supermassive black hole's event horizon is so far from the singularity that tidal forces there are mild. This has important implications for what happens when you fall into a black hole, which we will explore in detail. But it also means that the event horizon is not necessarily a place of violence. For a supermassive black hole, crossing the event horizon could be gentle, uneventful, marked only by the realization that return is no longer possible. Now let us consider rotation. Black holes can spin, and spinning black holes have more complex structure than the simple Schwarzschild black holes we have been discussing. A rotating black hole is described by the Kerr solution to Einstein's equations, named after Roy Kerr, who discovered it in 1963. A rotating black hole has two event horizons, an outer and an inner. Between them is a region called the ergosphere where space-time is dragged around by the black hole's rotation. In the ergosphere, it is impossible to remain stationary. Space-time itself is rotating, and everything in it must rotate too, regardless of how hard it tries to stay still. The ergosphere exists outside the outer event horizon, so escape is still possible from there. But the experience would be strange. You would be forced to orbit the black hole, dragged by the rotation of space-time itself, unable to hover or remain at rest. Black holes formed from collapsing stars are likely rotating, perhaps rapidly, because conservation of angular momentum means that the rotation of the original star is amplified as it collapses. The rotation rate is limited by the speed of light. If a black hole spins too fast, the event horizon disappears, leaving a naked singularity. General relativity allows this mathematically, but cosmic censorship conjecture suggests nature prevents naked singularities from forming. Black holes cannot spin faster than a certain maximum rate, called extremal rotation. Black holes cannot spin faster than a certain maximum rate, called extremal rotation. Sagittarius A, the supermassive black hole at the center of the Milky Way, is believed to be rotating but probably not extremely. Measurements of its spin are difficult but suggest moderate rotation. Other supermassive black holes show evidence of rapid rotation based on observations of their accretion disks and jets. Rotation adds complexity but does not change the fundamental property of the event horizon. It is a one-way boundary. Inside the outer event horizon of a rotating black hole, escape is still impossible. The rotation creates additional structure, including the ergosphere and potentially interesting physics near the inner horizon, but the basic inescapability remains. Electric charge adds another layer of complexity. Black holes can theoretically carry electric charge, described by the Reissner-Nordstrom solution for non-rotating charged black holes or the Kerr-Newman solution for rotating charged black holes. Charged black holes have inner and outer event horizons, and the physics between them is exotic, potentially involving exotic effects like closed time-like curves. But in practice, astrophysical black holes are probably not significantly charged. Any charge would quickly neutralize through interaction with surrounding matter. The cosmos is electrically neutral on large scales. A charged black hole would attract oppositely charged particles and repel like charged particles until it became neutral. So while charged black holes are mathematically interesting, they are probably not common in nature. What matters most for understanding the darkness of black holes is the event horizon, the boundary where escape becomes impossible. This boundary exists for all black holes, rotating or not, charged or not. It is the defining feature, the surface of no return, the edge of the darkness. It is the defining feature, the surface of no return, the edge of the darkness. And the darkness is absolute. A black hole does not emit light. It does not reflect light. It is not a black object in the sense of something dark-colored. It is literally a hole in space-time, a region where light cannot originate and from which light cannot escape. The only light associated with black holes comes from their surroundings, the accretion disk of matter spiraling inward, the jets of particles accelerated to near light speed, the stars and gas clouds that orbit nearby. The black hole itself is absolutely dark. This darkness persists forever, or nearly forever. According to classical general relativity, black holes are eternal. Once formed, they never disappear. They can merge with other black holes, growing larger. They can accrete matter, gaining mass. But they cannot shrink or evaporate or fade away. But quantum mechanics adds a twist. In 1974, Stephen Hawking discovered that black holes are not entirely black. They emit radiation, now called Hawking radiation, through a quantum mechanical process that occurs just outside the event horizon. This radiation carries energy away from the black hole, causing it to slowly evaporate. The process is extraordinarily slow for astrophysical black holes. A stellar mass black hole would take roughly 10 to the power of 67 years to evaporate completely. That is a 1 followed by 67 zeros, a time span vastly longer than the current age of the universe. A supermassive black hole would take even longer, approaching 10 to the power of 100 years for the largest ones. These timescales are so immense they are essentially forever. The universe will change beyond recognition long before any astrophysical black hole evaporates. Stars will die, galaxies will disperse, the cosmic microwave background will cool to near absolute zero, and still, black holes will remain. The cosmic microwave background will cool to near absolute zero, and still, black holes will remain. dark and massive, the last remnants of the stellar age. Only in the unimaginably distant future, when the universe has expanded and cooled to the point where black holes are the only significant structures remaining, will Hawking radiation become important. Then, slowly, over timescales that make the current age of the universe seem like an eye blink, black holes will evaporate, releasing their mass energy back to the universe as a thin wash of thermal radiation. But for any practical purpose, for any timescale relevant to human civilization, or even to the lifetime of galaxies, black holes are permanent. Once formed, they persist. Once matter crosses the event horizon, it is gone from the observable universe forever, or as close to forever as makes no difference. This permanence is part of what makes black holes so dark. They are not just dark in the sense of not emitting light. They are dark in the sense of being places where things disappear forever, where information is lost, where the normal rules about conservation and reversibility break down. Or do they? The information paradox, which we will explore later, asks whether information that falls into a black hole is truly lost or somehow preserved in subtle correlations in the Hawking radiation. This remains one of the deepest unsolved problems in theoretical physics, touching on the foundations of quantum mechanics and general relativity. For now, what matters is that black holes represent the ultimate darkness, places where light cannot escape, where matter disappears from view, where the future is constrained to a single outcome, arrival at the singularity, where space-time itself is warped so severely that the normal relationships between cause and effect, between past and future, break down. These are not abstract mathematical curiosities. These are not abstract mathematical curiosities. They are real objects scattered throughout the universe. Billions of stellar mass black holes in our galaxy alone. Supermassive black holes at the centers of most large galaxies. Possibly primordial black holes from the early universe. And perhaps intermediate mass black holes in dense star clusters. Each one is a tear in spacetime, a one-way door, a place of absolute darkness from which nothing returns. And understanding what it would be like to approach and enter such a place requires confronting the most extreme physics imaginable, the kind that pushes human intuition to its breaking point and beyond. The darkest places in the universe where nothing escapes. Part 3. Section 3. Falling into a black hole, the journey's end. Imagine you are falling toward a black hole, not by accident, but deliberately, in a spacecraft equipped with instruments to measure what happens as you approach the point of no return. You want to understand what crossing the event horizon actually feels like, what you would observe, what would happen to your body as gravity becomes overwhelming. This is a one-way journey. There is no return, but the knowledge gained might be worth the ultimate price. Your spacecraft approaches from a safe distance, moving slowly at first. The black hole itself is invisible against the darkness of space, but you can see its effects. Stars behind it appear distorted, their light bent by the intense gravity. Some stars that should be hidden appear around the edges of the black hole as their light is curved around it. This is gravitational lensing, and it creates a halo of distorted starlight surrounding the darkness. Imagine you are falling toward a black hole, not by accident, but deliberately, in a spacecraft equipped with instruments to measure what happens as you approach the point of no return. You want to understand what crossing the event horizon actually feels like, what you would observe, what would happen to your body as gravity becomes overwhelming. This is a one-way journey. There is no return, but the knowledge gained might be worth the ultimate price. Your spacecraft approaches from a safe distance, moving slowly at first. The black hole itself is invisible against the darkness of space, but you can see its effects. Stars behind it appear distorted, their light bent by the intense gravity. Some stars that should be hidden appear around the edges of the black hole as their light is curved around it. This is gravitational lensing, and it creates a halo of distorted starlight surrounding the darkness. As you fall closer, the lensing becomes more pronounced. The entire sky appears to distort, stars shifting and smearing as light paths curve through the warped space-time. Behind you, the universe appears compressed into a shrinking circle. Ahead, the darkness grows, swallowing more and more of your view. If the black hole has an accretion disk, matter spiraling inward and heating to millions of degrees, you see spectacular light shows. The disk appears warped and twisted by gravitational lensing. Light from the far side of the disk curves up and over the black hole, appearing above where it physically originates. The disk is extraordinarily bright, outshining entire galaxies, powered by gravitational energy as matter falls inward. But let us consider a simpler case, a black hole without an accretion disk, isolated in empty space. Just you, your spacecraft, and the invisible gravitational well ahead. But let us consider a simpler case, a black hole without an accretion disk, isolated in empty space. Just you, your spacecraft, and the invisible gravitational well ahead. The first physical effect you notice is tidal forces. Gravity decreases with distance from the source. Your feet, closer to the black hole than your head, experience stronger gravitational pull. This difference in pull across your body is called a tidal force, the same effect that causes ocean tides on Earth from the moon's gravity. For a stellar mass black hole, tidal forces become lethal long before you reach the event horizon. At a distance of perhaps a few hundred kilometers, the difference in gravitational pull between your head and feet exceeds what your body can withstand. You are stretched lengthwise and compressed sideways, a process gruesomely named spaghettification. The stretching accelerates as you fall closer. Your bones break, your tissues tear, your body is pulled apart into a thin stream of atoms, still falling inward but no longer recognizable as a human form. Death comes from mechanical destruction before you ever cross the event horizon. But for a supermassive black hole, the story is different. The event horizon is so far from the singularity that tidal forces at the horizon are mild. For a billion solar mass black hole, tidal forces at the event horizon are comparable to what you experience standing on Earth. You could cross the event horizon intact, alive, conscious. This is one of the strange paradoxes of black holes. The less massive ones kill you before you enter. The more massive ones allow you to enter alive, only to destroy you later when you get close enough to the singularity that tidal forces become overwhelming regardless of the black hole's total mass. The more massive ones allow you to enter alive, only to destroy you later when you get close enough to the singularity that tidal forces become overwhelming regardless of the black hole's total mass. Let us assume you are falling into a supermassive black hole. You approach the event horizon, instruments monitoring the gravitational field, your clock comparing its rate to clocks far from the black hole. Time dilation becomes measurable. Your clock ticks normally from your perspective, but compared to distant clocks, it runs slower and slower. At the event horizon, from the distant perspective, your clock stops. But you do not notice anything special. Your clock ticks normally. Your heartbeat is regular. Instruments show increasing gravitational pull, but nothing discontinuous, no barrier or surface. And then you cross. The event horizon passes through your spacecraft. Nothing changes visibly. There is no flash of light, no sensation of transition. The crossing is smooth and uneventful. But something fundamental has changed. You are now inside. Return is impossible. From your perspective, the universe behind you changes. The light from distant stars becomes blue shifted as you fall into the gravitational well. The stars appear to shift and compress further. Time in the outside universe, from your perspective, appears to accelerate. You see distant events unfold rapidly as gravitational time dilation works in reverse from the inside perspective. Ahead, the darkness deepens. You are falling toward the singularity, and that fall will end in finite time. For a supermassive black hole, you might have hours or even days before reaching the center. For a stellar mass black hole, seconds or minutes. As you fall deeper inside, tidal forces grow. What was negligible at the event horizon becomes noticeable, then uncomfortable, then lethal. What was negligible at the event horizon becomes noticeable, then uncomfortable, then lethal. The process of spaghettification that killed victims of stellar black holes outside the event horizon now occurs inside for the supermassive black hole. The stretching intensifies. Your body is pulled longer and thinner. Molecular bonds break. Atoms are torn apart. You cease to exist as a coherent object long before reaching the singularity. The matter that was you continues falling as a stream of particles, each doomed to reach the center. And at the singularity, general relativity predicts infinite tidal forces, infinite space-time curvature, complete breakdown of physics. But these infinities signal the theory's limits, not physical reality. Quantum gravity effects, whatever they are, must become important before the true singularity is reached. What actually happens at the center remains unknown. Perhaps space-time is quantized at the smallest scales, preventing true infinite compression. Perhaps the singularity is avoided by quantum tunneling to another region of space-time. Perhaps multiple universes branch off at the singularity, or wormholes connect to distant regions of our universe. These are speculations. The event horizon prevents any observations that could confirm or refute them. Whatever happens at the singularity remains hidden behind the one-way boundary, unknowable from outside, experienced only by matter that can never report back. From the outside perspective, your fate is different. Distant observers see you fall toward the event horizon, slowing asymptotically as time dilation becomes extreme. Your image freezes at the horizon, redshifting to invisibility over a span of time that, from the outside, appears infinite. You never cross from their perspective. You remain frozen at the event horizon forever. You never cross from their perspective. You remain frozen at the event horizon forever. Your last photons stretched to infinite wavelength. Your information seemingly preserved at the boundary, even though you crossed and died from your own perspective. This is the black hole's ultimate paradox. Two equally valid descriptions that cannot be reconciled. From outside, you never enter. From inside, you enter and die quickly. Both are true in their reference frames, and the event horizon is the boundary that prevents these contradictory truths from creating paradoxes. The journey into a black hole is one way, ending at the singularity in unknowable destruction. The darkness is complete, the isolation absolute. Nothing that crosses the event horizon ever returns, ever communicates with the outside universe, ever escapes the inevitable pull toward the center. This makes black holes the darkest places imaginable. Not just dark to light, but dark to all forms of communication, all possibility of rescue or escape, all connection with the universe beyond the boundary. A cosmic prison from which not even information can break free. Or can it? Hawking radiation and the information paradox suggest otherwise, as we will explore next. Stephen Hawking discovered in 1974 that black holes are not completely dark. Through quantum mechanical effects at the event horizon, they emit faint thermal radiation, now called Hawking radiation. This discovery united quantum mechanics, general relativity, and thermodynamics in an elegant framework that revealed black holes have temperature and entropy. It was one of the most profound insights in theoretical physics, suggesting that even the darkest places in the universe glow, however faintly. The mechanism is subtle and deeply rooted in quantum mechanics. According to quantum field theory, what we call empty space, the vacuum, is not truly empty. It seethes with activity at the smallest scales. Virtual particle-antiparticle pairs constantly pop into existence throughout space, borrowing energy from the vacuum for brief instants allowed by Heisenberg's uncertainty principle. These pairs exist for such short times that they cannot be directly observed. They exist for perhaps 10 to the power of negative 21 seconds, and then annihilate, returning their borrowed energy to the vacuum. Normally, these quantum fluctuations have no observable macroscopic effect. The particles are virtual, meaning they exist only as temporary violations of energy conservation permitted by quantum uncertainty. They do not carry energy away from any system. They simply fluctuate and disappear. But near the event horizon of a black hole, the extreme curvature of space-time changes this picture. If a virtual particle pair appears just outside the event horizon, quantum fluctuations at the boundary between inside and outside can have dramatic effects. One member of the pair might fall across the event horizon while the other escapes to infinity. From the perspective of a distant observer, it appears that the black hole has emitted a particle. This is Hawking radiation. The escaping particle is real, not virtual. It carries energy away from the black hole, and that energy must come from somewhere. The source is the black hole's mass. Through the equivalence of mass and energy established by Einstein's E=mc², reducing the black hole's mass slightly provides the energy for the emitted particle. Each Hawking radiation emission reduces the black hole's mass by an infinitesimal amount. Over time, this accumulates. The black hole slowly evaporates. Each Hawking radiation emission reduces the black hole's mass by an infinitesimal amount. Over time, this accumulates. The black hole slowly evaporates. The energy for the emitted particle comes from the black hole's mass. Each emission reduces the black hole's mass infinitesimally. Over immense timescales, this causes the black hole to evaporate. Smaller black holes radiate more intensely because their surface gravity is stronger. A stellar mass black hole evaporates in roughly 10 to the power of 67 years. A supermassive black hole takes 10 to the power of 100 years or more. These times are incomprehensibly vast. The current universe is only about 10 to the power of 10 years old. Black hole evaporation happens on timescales trillions of times longer than the age of the cosmos. For all practical purposes, astrophysical black holes are permanent. But the existence of Hawking radiation creates profound theoretical problems, particularly the information paradox. Quantum mechanics says information cannot be destroyed. But if black holes evaporate into featureless thermal radiation, where does the information about what fell and go? This paradox has driven decades of theoretical research. Possible solutions include information encoded in subtle correlations in Hawking radiation, information preserved at the event horizon in a firewall of high-energy particles, information stored in a holographic encoding on the event horizon surface, or violations of quantum mechanics in extreme conditions. The resolution remains uncertain, representing one of the deepest unsolved problems in physics. But what is clear is that black holes, while nearly perfectly dark, are not absolutely dark. They glow faintly with quantum radiation, slowly returning their mass to the universe over timescales that dwarf all human comprehension. They glow faintly with quantum radiation, slowly returning their mass to the universe over timescales that dwarf all human comprehension. Eventually, in the unimaginable far future, every black hole will evaporate. The final moments of a black hole's life are dramatic. As it shrinks, it radiates more intensely. The last stages occur rapidly, a burst of gamma rays and particles as the final mass converts to radiation. Then nothing remains but the radiation dispersing into space. This is the ultimate fate of the darkest places in the universe. Not permanent, but temporary on cosmic scales, lasting for periods that seem eternal but eventually yielding to quantum evaporation. The darkness is profound but not forever. Black holes represent the most absolute darkness, but they are not alone. The universe contains other regions of profound darkness, places where light is absent or trapped, where cold and isolation reign. Cosmic voids are immense regions of space containing few or no galaxies, stretching hundreds of millions of light years across. These are the largest structures in the universe, vast empty bubbles in the cosmic web where matter is extraordinarily sparse. A traveler in a cosmic void would see almost no light, no nearby stars or galaxies, just darkness punctuated by rare distant glimmers. Tidally locked exoplanets orbiting close to red dwarf stars present one face perpetually toward their sun and the other face perpetually away. The dark side experiences eternal night, never seeing starlight, potentially reaching temperatures near absolute zero. These frozen nightside hemispheres are dark beyond imagination, lit only by faint starlight or possible volcanic activity. The outer reaches of planetary systems, beyond the frost line where sunlight becomes vanishingly faint, harbor darkness on a smaller scale. The outer reaches of planetary systems, beyond the frost line where sunlight becomes vanishingly faint, harbor darkness on a smaller scale. The Kuiper Belt and Oort clouds surrounding our solar system extend thousands of times farther from the sun than Earth, where sunlight is no brighter than starlight and billions of icy bodies drift in perpetual twilight approaching true darkness. Deep beneath the surfaces of ocean worlds, darkness is absolute. Europa's subsurface ocean, miles beneath its icy crust, receives no sunlight. Enceladus' hidden sea, warmed by tidal heating, exists in complete darkness. These environments might harbor life adapted to darkness, ecosystems powered by chemical energy rather than photosynthesis, thriving where light never penetrates. Even within planets, darkness reigns. The core of Jupiter, crushed under millions of atmospheres of pressure, is dark despite temperatures exceeding that of the sun's surface. The center of Earth, thousands of kilometers below the surface, is dark and will remain so for billions of years. These dark places, while profound, lack the absolute finality of black holes. Light could reach them given a source. Information can escape. They are dark by circumstance, not by fundamental physics. Black holes alone represent inescapable darkness, regions from which light, matter, and information cannot return. They stand as cosmic monuments to the limits of physics, the boundaries beyond which our universe becomes unknowable. The darkness they represent is not merely the absence of light, but the presence of an absolute barrier, a one-way membrane in space-time that nothing can cross in reverse. Black holes represent more than physical darkness. They embody ultimate limits, absolute boundaries, points of no return that resonate with deep human concerns about control, knowledge, and finality. Black holes represent more than physical darkness. They embody ultimate limits, absolute boundaries, points of no return that resonate with deep human concerns about control, knowledge, and finality. The event horizon is a threshold beyond which rescue is impossible. Communication ends. Information is lost. It represents the ultimate one-way door. This resonates with human experience of irreversible choices, moments after which return is impossible. Death itself is sometimes described as crossing an event horizon, a boundary beyond which no information returns, no reversal is possible. But black holes differ from death in important ways. They are mathematical objects, describable by precise equations, predictable in their behavior. We understand them even though we cannot experience them in return. They are mysterious in their interiors, but not in their existence or essential properties. This suggests that some limits, while absolute, can be understood. The event horizon cannot be crossed in reverse, but its location can be calculated. The singularity cannot be observed, but its inevitability follows from well-tested physics. Black holes teach us that boundaries can be absolute while still being comprehensible. There is strange beauty in this. The most extreme objects in nature, places where physics reaches its limits, are also among the most precisely understood. We cannot visit the center of a black hole and return, but we can model it, predict it, understand its role in the cosmos. Black holes also embody absolute loss. When something crosses the event horizon, it is gone from the observable universe, not hidden temporarily, but removed permanently from all possible interaction. This represents the only true irretrievable loss in the cosmos. Or does it? The information paradox suggests maybe not. Or does it? The information paradox suggests maybe not. Perhaps information is preserved in Hawking radiation, or encoded on the event horizon, or connected to the outside through subtle quantum correlations. The final answer remains unknown, but the question itself reveals that absolute loss might violate quantum mechanics. Physics may not permit true destruction of information, even in black holes. This tension between general relativity and quantum mechanics at the event horizon points toward deeper theories still undiscovered. Black holes are cosmic laboratories where our best theories conflict, demanding resolution, forcing us to develop better frameworks that can encompass both quantum mechanics and gravity. In this sense, black holes illuminate even as they darken. They reveal the limits of current understanding and point the way toward deeper knowledge. The darkness they represent is not intellectual darkness, but physical darkness surrounding intellectual light. For human consciousness, black holes offer perspective. They demonstrate forces beyond control, limits beyond transgression, boundaries that cannot be negotiated or circumvented. They remind us that some things truly are impossible, not merely difficult. You cannot escape from inside the event horizon. This is not an engineering challenge. It is a structural feature of space-time itself. Yet we exist far from any event horizon, safe in a universe where escape is possible, where time flows forward, where the future remains open. Black holes define the boundaries, but we live in the interior, the vast open spaces where matter can move freely and light can travel unimpeded. The darkest places in the universe exist, but they are rare and specific. Most of space is not dark in this absolute sense. Most of the cosmos permits light, motion, escape. The darkness is real but localized. Most of the cosmos permits light, motion, escape. The darkness is real but localized. And even the darkness serves purposes. Black holes likely played crucial roles in galaxy formation. They regulate star birth in galactic centers. They create some of the universe's most energetic phenomena through their accretion processes. The darkness at their centers is surrounded by brilliant illumination from infalling matter. As you drift towards sleep now, consider this: the same universe that contains black holes, the most extreme and unforgiving objects imaginable, also contains stars, planets, and life. The same physics that permits event horizons also permits consciousness. The darkness and the light are both parts of the cosmic story, both necessary to the whole. And in your sleep, you enter your own darkness, a safe darkness of unconsciousness from which you will emerge. Not an event horizon, but a natural cycle. Not absolute, but temporary. Not a prison, but a refuge. The darkest places in the universe teach us about extremes, about limits, about the nature of space-time itself. They stand as monuments to physics at its most fundamental and most strange. They represent regions where normal intuitions fail completely, where only mathematics can guide understanding. But understanding is possible. Even across the vast distances that separate us from black holes, even across the absolute barrier of the event horizon, we can know them, model them, predict them. The darkness is profound but not impenetrable to thought, to mathematics, to the human drive to comprehend. And so the darkest places in the universe, where nothing escapes, become paradoxically sources of light, of knowledge, of insight into the deep structure of reality. They show us our limits while simultaneously showing us how far understanding can reach beyond experience. They show us our limits while simultaneously showing us how far understanding can reach beyond experience. The journey into darkness reveals light. The places of no escape teach us about freedom. The regions of absolute finality illuminate the nature of time, space, and causality themselves. These are the darkest places in the universe. Understand them, and you understand something profound about reality itself. Fear them if you must, but also admire them, study them. Let them guide you toward deeper knowledge of the cosmos and your place within it. And now, let that knowledge settle. Let the images of darkness and light mingle in your mind as consciousness fades into the temporary darkness of sleep, the safe and natural darkness from which you will wake to face another day in a universe that contains both the brightest stars and the darkest voids, both the freedom of open space and the inescapable pull of event horizons. Rest now, knowing that the darkest places are far away and the light, for now, is yours to experience. Tomorrow brings new photons, new experiences, new journeys through a universe vast and strange and beautiful in all its darkness and light.